All right. So we're starting off with solution. And remember, I do not give definitions, but you do need to be able to give examples or recognize examples of these, okay? So a solution, another way to say solution is a homogeneous mixture. A homogeneous mixture. A solution is a homogeneous mixture. A solution is made up of a solute and a solvent. It contains both a solute and a solvent. And the solute is the substance being dissolved. The solvent is the substance doing the dissolving. So it is the substance doing the dissolving. All right. So if I had salt water, did you go to the ocean, Lucas? Wasn't that cool? That's pretty cool. All right, so that's awesome. Is that your first time at the ocean? Nope, ocean's great. So what is the ocean made up of? Salt water. So in the ocean, what is the solute? Salt. The salt. What is the solvent? Water. Okay, so the ocean is a solution of salt water. That's what the ocean is. The ocean is a solution of salt water. So it's got the solute, which is the salt, and the solvent, which is the water. So perhaps you make hot tea or cold tea. Let's say you make sweet tea. So what is the solute? Sugar and the tea extract. What is the solvent? The water. The water is the solvent. And so you probably have a pretty good idea of solute and solvent, maybe just never use those words. So make sure that you know those words and what they are. And if I give you a solution, you could tell me which is the solute and which is the solvent, that you understand that. All right, the term solubility. The term solubility means, or the basically what solubility means, is the amount of solute that will dissolve in a specified amount of solvent under stated conditions. The amount of solute that will dissolve in a specified amount of solvent under stated conditions. Solubility is expressed in a solubility graph, a solubility curve, a solubility chart. So I'm just going to make a little note here, expressed in graphs, charts, tables. The solubility of a substance will be expressed in a graph, a chart, or a table. Do you have anything in these notes that expresses solubility? Yes or no? Yes, you do. What do you have in these notes? What's it say, guys? Read it. Solubility graph. You have a solubility graph. And so let's look at that solubility graph. Let's look at the solubility graph. Let me come out just a little bit. Let's look at that solubility graph. So what do you see in the top left? It says NaCl, it's in blue, KCl in red, sucrose in green. That means each of these lines represents those substances. On the left-hand side, and I know this is small, that's why I zoomed it in. On the left-hand side, it says solubility in water, grams per liter. That means the number of grams dissolved per liter of water. On the bottom, it says temperature in degrees Celsius. Now let's go back to the solubility term. Solubility says the amount of solute, are these solutes? Yes, the amount of solute dissolved in a specified amount of solvent. What is the specified amount of solvent? How much? It's right over here. Know the amount of solvent. Liter, 1 liter. So it's the amount of solute, which is going to be in grams, in 1 liter of solvent under stated conditions. What are our conditions? Temperature. And then what we find out is that potassium chloride, which is the red line, potassium chloride, what would you get? Tell me about what you see about potassium chloride. What would you say the solubility of potassium chloride is at 70 degrees Celsius? It's this line, it's the top line down at the bottom. What is the solubility of potassium chloride at 70 degrees Celsius? Is it right at 500 grams? This is 0, 500, 1,000, 1,500, 2,000. So do you say 500 grams? Best you can see, right? So in other words, 500 grams of potassium chloride, this is the solubility of potassium chloride. Remember, it's the amount of solute in a specified amount of solvent at stated conditions or under stated conditions. So the solubility of potassium chloride is 500 grams of potassium chloride will dissolve in 1 liter of water at 70 degrees Celsius. Now, what happens if the temperature increases to 100 degrees Celsius for potassium chloride? The solubility increases. In other words, can more grams be dissolved? Yes. Now, is it a huge difference or a small difference? Small difference. Now, let's go to sucrose. What is sucrose? In the real world, what's sucrose? Sugar. Regular table sugar. That's what sucrose is. So when you look at sucrose, whoa, what do you see with sucrose? Which means what? That curve, what's that mean? What's that tell us about sucrose? What changes the solubility of sucrose very well? Temperature. Increased temperature, solubility drastically increases. This is something that is so obvious if you've ever tried to make rock candy. And we're going to talk about rock candy in just a minute. But it's also, I've had students in the past who, and it's been a long time since they said this, but I can't remember when it was, but it's a long time ago, I had a student tell me that they had a saturated sweet tea solution, that they put so much sugar in their sweet tea that they made it saturated. And I was like, no way could you make it saturated. It might be super sweet, but it's not saturated. Well, how do I know that? Because, and we haven't even gotten to that word yet, but saturated is what you read off the solubility chart. A saturated solution is what you're reading, and I'll write something here in you just a minute. But saturated is what you're reading off the solubility chart. So let me pick a number. At 20 degrees Celsius, which is right here, at 20 degrees Celsius, how many grams of sucrose, how many grams of table sugar will dissolve in 1 liter of water? 2,000 grams. 2,000 grams of sucrose will dissolve in 1 liter. 1 liter. This is 700 milliliters. So that's close. I would bet your white water bottle is close to a liter. That's close to a liter. 2,000 grams. How many grams are in a pound?
6 4
That's 4.4 pounds. We have a little, what? What? Let's make sure we're reading this right. Let's make sure we're reading this right. 2,000 grams per liter. 2,000 grams right there. 20 degrees Celsius. 20 degrees Celsius is cool room temperature. Kind of like, I would have to do the math here. Yeah, 68 degrees Fahrenheit. So that's cool room temperature, right? 68 degrees Fahrenheit is 20 degrees Celsius, 2,000 over 4 pounds, almost 4.5 pounds of sugar. Do you know what a bag of sugar looks like? The smallest bag, that's 4 pounds. That's a 4-pound bag of sugar. A 4-pound bag of sugar can dissolve at this room temperature, cooler than this room temperature right now, water. Is that crazy? And that would be saturated. So what do you see then happening? As the temperature goes up, does it super increase? Yeah, that's amazing. Would you say that sucrose is very, very soluble in water? Now, what would you say about sodium chloride? Sodium chloride is down here, and it's the blue line, and it pretty much stays the same across the board. That means what? Does temperature have an influence really on sodium chloride dissolving? No. Is sodium chloride as soluble as sucrose? Not at all. And if you've ever tried to make a salt water solution, you've seen that. It just doesn't mix up super well. I mean, it dissolves, but it doesn't dissolve really, really well. And it becomes saturated very quickly, which is what's evident here. It doesn't take much. And so when we're talking about solubility, I use this term that I struggled with. It's all relative. Solubility is all relative, meaning the solubility of a substance is related to its temperature and how much water it's being dissolved in, or how much is already dissolved. Because the more that's already dissolved, will it take longer for the extra to dissolve? Does that make sense? Think about that again. The more you have in it already, would it take longer for the new solute to dissolve? If it already has some in it, and it does. It does. It takes even longer. So in other words, like for instance, if you were making either sodium chloride solution or a sucrose solution, let's say you'd already put your 4 pounds of sugar in there and you started heating it up. Is it going to take a little, or let's go backwards. First pound of sugar in the water. Will that dissolve pretty quickly? Yes. Second pound of sugar, will it take a little longer? Third pound of sugar, but will it dissolve eventually? Yes. What do you need to do to make things dissolve? Stir. Agitation. Stirring. Agitation, as well as heating up things that it can also help if needed. But in this case, it's not needed. All right, so let's look at what saturated is. Saturated is the maximum amount of solute dissolved in solvent under stated conditions. Maximum amount of solute dissolved in solvent under stated conditions. Don't make this one hard. What's unsaturated? Less than. Less than the maximum amount of solute that could be dissolved. Less than. In other words, less than saturated. It's less than saturated. And then what do you think supersaturated is? More than. Supersaturated, and then you're like, well, how can you get more than? Well, I'll show you. Supersaturated is more than the maximum amount of solute dissolved. Supersaturated is more than the maximum amount of solute dissolved. In order to supersaturate the solute or solution must be heated, solute added, then solution cooled slowly. Have any of you ever made rock candy? Has anybody ever made rock candy? Have you made it? Can you make it? I can't make it. I cannot make it. So how do you make your rock candy? Tell me how to make it. So you put equal parts?
Yeah.
Okay.
And then you don't stir it, just let it do its own thing. So it gets like usually make apple flavor and color, and then heat it again without stirring it, and then just like pour it in.
So what's the point of, so that's interesting, you don't stir it. I've never heard that before. So you just do you let it boil? So you let it boil
It's not like a rolling, but like just about to.
just enough to dissolve it.
Yeah.
Just enough to dissolve it. So did you hear what she said at first? Equal parts. That's probably where I mess up. I probably put too much sugar every time I've tried to make it. So let's go back though. What did we just learn about sucrose? What'd you just learn? In 1 liter of water, over 4 pounds will dissolve. Does that make sense? So in order to make it super saturated, you have to put more than 4.5 pounds in that 1 liter of water. Yes? And so how do you get more than 4.5 pounds to dissolve in 1 liter of water? Well, that was at 20 degrees Celsius, correct? So what happens if you heat it up? What if you heat your water up? Will more dissolve? Yes? But what is room temperature? So in other words, let's say that you heated it up to, because she said you get it to close to boiling or right at boiling. But let's say, okay, we're going to just stop it at 80 degrees Celsius, which is before boiling, but pretty good and hot. Okay? And let's say it's all dissolved. Is 80 degrees Celsius warmer than room temperature? 100 degrees Celsius is 212 degrees Fahrenheit, right? Okay. So is 80 degrees Celsius warmer than room temperature? Yes. So, but we're cooling it back down to room temperature. So in other words, let's say that we have 1 liter of water, and let's say that instead of 4.5 pounds of sugar, we add 5 pounds of sugar, or 5.5 pounds of sugar in 1 liter of water. You follow me? That should easily dissolve at 80 degrees Celsius, correct? Yes or no? Okay. But what should only be dissolved at room temperature? Only the 4.5 pounds. But how much did we put in it? Wake up, Ryan. How much did we put in it, though? 5.5 pounds. So what does that mean? Once we cool it down to room temperature and it's still in solution, have we made a supersaturated solution? Yes, yes. Now, how do you get it to crystallize out? How do you do it?
We can either like put it on the tray or like how I did it when I was little, because we coated a stick in sugar and stuck it in.
So if you take a stick that has, and sometimes it just works with just a stick itself. What you have to do is you have to put something in the solution to make it crystallize out, and you have to give it an extra. It's kind of like you've got to give it a starter or a seed. You're kind of like giving it a seed to have something to crystallize out on. And that's the point of the stick or a string. And I've never heard of anybody putting sugar on it, but maybe that also helps because you're adding something that's already in it to kind of attach back to it. So I'm assuming you would wet the stick first, roll it in sugar, and then stick it into the solution you've made. The solution you've made is like syrup at this point. The solution is syrup. How many of you have ever seen rock candy? Typically, if you go to like a state park or a national park, you can buy rock candy on a stick. Yes, and so that would be then, it's going to be crystals of sugar on a stick. And how it's made is what we're talking about. It's a supersaturated solution. Now, there is another supersaturated solution that is a little different than this, but it's also a supersaturated solution, and it has to do with hand warmers. Have any of you ever seen the liquid hand warmers that are in bags? Not the hot hands, which is iron, that you open up and expose to air, and then it becomes the iron 2 oxide. We're not talking about the ones that have the powder in them. I'm talking about the liquid. Have any of you ever seen the bags of liquid? What does it have in it? What is that bag? It's like a little bag about this size. It's about the size of a sandwich bag, a really thick plastic with a liquid inside of it. And what does it have inside that liquid? Do you remember? You don't remember? Does anybody know? A little metal disc. It's a little metal disc. And what do you do to, let me give you a visual or a knowing what that, do you remember on a pickle jar, or if your mom ever did canning, or any jar that's sealed, you open the sealed jar up and it pops, you know what I'm talking about? But then once you put it back on, you can push it and it goes up and down, you know what I'm talking about? Okay, that little disc inside this bag I'm talking about can push up and down. You can click it. So what you do is, inside this bag is a supersaturated sodium acetate solution. Read the bag, go find one. They used to sell them in the mall during Christmas time. They also, I've seen them being sold at Sam's at Christmas time. I don't go in the much or Sam's much. I don't go shopping much during Christmas time in buildings. So I don't know if they still do it or not, but you could also look them up. But it's liquid hand warmers in bags, and the liquid is supersaturated sodium acetate. And inside of it is that little disc, that little click. You can click it. It's about the size of a penny, and it clicks. You give it its activation energy when you click it. And when you click it, it starts to crystallize out. And as it crystallizes out, it gets hot. It gets warm. Because that's a property of supersaturated sodium acetate. And the beauty of those little hot packs is you can reuse them. Because all you have to do is what? To make it back to where it was. What do you have to do? To make it back to where it was. How did it get there to begin with? How did they make that supersaturated solution to begin with? Heated it up. So you put it in a bowl of hot water, or put it in a pan of boiling water, or put it in the microwave in water and heat the water up, boil the water, and guess what that solution does? Goes back into solution. And then you can click it again and do it again, click it again, and it's reusable. And it'll last for a very long time, able to do that because it's its own closed system. That's a supersaturated solution. Very, very, and they work, I think, probably better than hot hands, especially the fact that they're reusable. I don't know why you don't find them that much. So, but it's a supersaturated sodium acetate solution. So I'm going to make a note here. And then there's another one in your house potentially, and they were giving some of this away the other day here in this building, that is a supersaturated solution. So I'm going to put rock candy, hand warmers, and I'm going to tell you what that one is. That's a supersaturated sodium acetate. Okay. So rock candy, hand warmers. Now, what could be in your pantry? What could be in your pantry? Something you eat that is a supersaturated solution. It's something in your pantry that you eat. Has to be a liquid. What kind specifically?
There's all kinds out there.
Maybe maple. I don't know on maple for sure. Honey. Honey. What do we do when the honey, what's the honey do occasionally at our house? Crystallize. What do you do to get that honey back into solution? What do I have you do? I have you put it in. I say don't throw it away. Put it in a jar or a bottle or a pan of warm hot water. And what does that honey do? Goes back into solution. So honey is I don't know if maple syrup does that or not. Have you ever seen maple syrup crystallize like that?
I know Treesap does it, so I assume.
I don't know for sure. I'm not sure. I don't know that. I've not seen that happen. Does it? Maple syrup, he says he's seen it happen. I would not be surprised because I feel confident it's pretty saturated, super saturated, because it's boiled down. In order to make maple syrup, you got to boil and boil and boil and boil and boil. So you boil off a lot of water off that tree sap to get it to be maple syrup. The other one, sorghum. Have any of you ever had sorghum molasses or molasses? You know what I'm talking about? That also is a super saturated solution. Yes, definitely. No, I know sorghum can, or honey, or
Syrup.
and syrup can too. I've never seen that because I don't buy it. So what we're going to do here is we're going to put honey. We can put molasses, maple syrup, and like you said, if you know that the other syrups do it, you now have an idea. I'm not going to list everything that does it, but you now have an idea. And now you also, when you have that happen at your house, don't throw the honey away, okay? Just stick it in some hot water, boil the water, and you'll have your honey back, okay? So maybe that's what you need to do to your loved one that isn't nice and kind anymore. Stick them in some hot water and you'll get your honey back. No, joking, okay? Y'all can't even find that honey. That funny. Honey, funny. Okay, all right. You need to lighten up. All right, so what does miscible mean? What does miscible mean? Anybody know? In this context of what we're talking about, miscible and immiscible. What does it sound like? Say it.
I think it would be separated.
Not quite. Miscible and immiscible. What does the word miscible make you think of? What are we doing to make solutions? Mixing. What does miscible mean? Mixable. So exactly what it means. Miscible means mixable. So if two solutions are miscible, they are mixable. If they're miscible, they're mixable. If they're immiscible, they are not mixable. This is improving your vocabulary, okay? So are honey and water miscible? Yes, they are. Honey is sugar water, basically. Is it going to mix with water? Now, will honey mix with oil? No, it's immiscible. Now, will it actually, well, I'm not going to get there because that's a cooking, I won't go there. Let's do oil and water. Are oil and water miscible? No, oil and water are immiscible. Immiscible. What about gasoline and oil? Are they miscible? Yes, gasoline and oil are miscible. They are both organic substances, carbon-based, and they are miscible. But oil and water are immiscible Gasoline and water are immiscible. Gasoline and water are immiscible. What about ethanol and water? Ethanol is the drinking alcohol. Ethanol and water, are they miscible or immiscible? Guys, think about that real carefully. Ethanol and water. Immiscible or miscible? Do you drink straight alcohol, those people who choose to drink ethanol? You drinking straight, 100% alcohol? No. What's it mixed with? Water. It's mixed with water. So your alcohol, which is ethanol, and water are miscible. You're not drinking straight ethanol. You're not drinking straight ethanol, okay? It's immiscible in alcohol is miscible in water. I forget immiscible. Alcohol has a property that allows it to be miscible in oil and water. And when you get into organic in 107, you'll get that. They're going to talk about that. So alcohol it's an intermediate solvent. It can dissolve both oil and water. And that's why alcohol, ethanol, is used for your extracts. Have any of you ever had vanilla extract, and real vanilla extract, and you read the bottle and it will say ethanol? It will say vanilla something, maybe vanilla bean and ethanol. And that's why it's in ethanol, is because then that ethanol will dissolve in water if you're using it in a water-based recipe, or it will dissolve in oil, because ethanol can do both. Ethanol can dissolve in both water and oil. So it is a miscible substance in both. All right, so 2 words there. All right, now then, what's the effect of temperature and pressure on dissolving? So it says temperature. With increased temperature, the solubility of solids, with increased temperature, in general, the solubility of solids what? Increases. With increased temperature, the solubility of solids increases. With increased temperature. With increased temperature, the solubility of gases. See how much you all know. I've got some fishermen in here. See how much you fishermen know. With increased temperature, the solubility of gases. What do you think, Nate?
Yes, decreases.
You're exactly right. It decreases. It decreases. With increased temperature, the solubility of gases decrease. Now let's think about that. Hot pond in the middle of the summer. I'm talking hot pond. Been above 100 degrees for many days. What starts to happen? Well, it evaporates, but what happens to the fish sometimes? I'm talking really hot, shallow pond. What happens? Die. The fish die. Fish die. Why do the fish die? Not enough oxygen. Why not? Because the water got too hot. The water got too hot. And when the water gets too hot, the fish die because the oxygen level decreases. That's one of the beautiful things about oxygen and water, is that in the wintertime, and this is also that beautiful property of ice floating, in the wintertime, why are the fish allowed, or why can they live so well? Because what is increased in the wintertime for the fish? Oxygen. The oxygen level is increased. This is also why when you think about the pipes bursting, this is part of why we have that situation happening. So you've got 2 scenarios going on the pipes bursting, okay? But I tell you what, we're not going to go there. I think it'd be easier just to leave it like we've already talked about it. That in water, so I'll just deal with what we dealt with already. And we've already mentioned this, so I'll reiterate what we mentioned. In your pipes, why do the pipes burst? Because the temperature decreases, the oxygen level would be increased, but what happens to the water itself as the temperature gets colder? It expands. And that's what causes then the pipe to potentially burst, because it can push on the pipe walls and cause the pipe to burst if it's under pressure. What about a fish tank? Have any of you ever had a fish tank with a heater in it? Anybody ever had that? Anybody? Nope. Has anybody had a fish tank with a heater? Have you ever turned the heater up? You ever killed fish because you turned the heater up? It's like you're like, oh, those fish must be cold. It's cold in that water. Oh, let's turn the heat up. Whoop, loading fish the next morning. Because those fish did not need that temperature increase, because as soon as you turn the increase up, what happens? They die because of lack of oxygen. Lack of oxygen. All right, does pressure affect the solubility of solids or liquids? What do you think? Pressure. Does the pressure affect, for instance, sugar dissolving in water? Pressure? No. Pressure doesn't affect liquids or solids dissolving. What does pressure affect? Gases. Tell me how you know that. What do you know in this world that is under pressure that has a gas in it? True, but we're not really talking about the dissolving of gases. You're very right. Sodas. Sodas, soft drinks. Soft drinks. What do those soft drinks have in them? That's a gas. Carbon dioxide. The soft drinks have carbon dioxide in them. And what does that carbon dioxide need in order to stay in solution? Pressure. It's kind of funny. I have a theory, and I have never tested my theory. Probably won't ever test my theory. But when I was a kid, I was born in 71. So in 70, I need to look it up. I don't know for sure when it happened. But when I was a little girl, the only way we could buy soft drinks were in glass bottles. And they were 16 ounce or I guess 8 ounce. I don't know for sure what they were. Nowadays you can still buy the smaller bottles. But used to, you could buy a 16 ounce, and I will just give you a little back history, just a little memory here. 16 ounce Dr. Pepper with real sugar, barely frozen. Best thing ever. You'll never have something better than that, okay? Just so you know. But didn't get it very often, but when I was a little girl, occasionally we would get those. As I grew older, they came out with a Pepsi can. And they started coming out with aluminum cans. And some of you may have seen the vintage cans with I think it's the blue and red Pepsi. That's what they used to look like when they first came out. And I don't know what year that was. I'm assuming it was sometime in the 70s. Because I remember going from glass bottles to cans. They didn't have cans when I was little bitty. I only remember glass bottles. Now, let's go back again. Let's go back. Bottles. Those glass bottles, there was no way to close them up. So on 4th of July, which is when I would get my ice cold Dr. Pepper. On 4th of July, when I was a little girl, we would have that ice cold Dr. Pepper. And I'm talking like I was just a little girl, like 5, 4, 6, 7, in that range. I remember not drinking the whole thing and wanting to save it, because we only got Cokes just occasionally, okay? So I wanted to save it, so I put it in the refrigerator. Tell me how it tasted the next morning. Flat. Why? Because all the carbonation came out, and then you're all disappointed. All right? Now, there was no way to close it up. So you either drank the whole thing or you didn't drink it. Most of the time, you just didn't drink it. And it was 16 ounces or 8 ounces. Now then, go to cans. Improvement as far as glass breakage, no problems there. Also, don't get your 10 cent or 5 cent deposit back, which is what you used to get on bottles because they would reuse them. Go to cans, though. Once again, you drink all of it, don't drink it, what happens? It goes flat. Then keep going, and I have no idea, I don't know for sure. I know then plastic bottles came out, but I don't remember when that was either. I'd have to look it up. Then, what'd they start to do? Plastic bottles that had what? Screw-on lids. Now, do you think people drink more soft drinks now or in the 70s and 80s? Now, by far. It's much, much more soft drink usage because of that. And so it's kind of interesting. It also makes you wonder, obesity. Is there more obesity because of is that one of the reasons for obesity. And then again, also, you could also go to the fast food. We didn't have supersized meals either back then. And so all that's changed. And so it's kind of interesting, though, when you look at that. And that's in my lifetime. That's in 50 years. I've seen that, which, golly, to think that's half a century is crazy. I'm really old when you think of it that way. But it's kind of funny for the fact that I've seen that change. And it's kind of an interesting thing. But it all goes back to right here. That's what it all goes back to. So with increased pressure, it increases the solubility of gases. So increased pressure, solubility of gases increases. And so I'm going to make a note here, soft drinks. I'm going to make a note there, soft drinks. Okay? And on this one, for the gases in temperature, I'm going to make a note here, hot water, dead fish. Okay? Hot water, dead fish. All right, now grab your calculator. Yes, Katie?
Math boxes are still the way to go.
They are good, I agree.
There are a few places you can get them.
There are, they're good too. All right, grab your calculator and let's get to working on the math. All right, what I want to do is I want to run through all of the different concentration units first today, and then we're going to start the math, okay? You have to know these formulas. You have to know how to do these, okay? This test is going to be a lot of math. Why? What was last week? What kind of math? What were those called? What problems were those? Gas laws? Gas law problems? Was that all pretty much math? A little bit of concept, but a lot of math? This is a little concept, a little more concept, but a lot of math, okay? So you've got to be ready for the math. You've got to practice all the practice problems that I'm giving you on Blackboard if you want to do well on this test. If you will do everything I've got on Blackboard for practice, guys, you will ace this test. And the actual amount that's comprehensive is not that much. This is so you can do well on this test, but if you don't practice your math, you'll bomb it and you'll affect your whole grade for the semester. It's up to you. You have the practice problems to do. All right, so you're going to do several different methods of calculating concentration. So one method of calculating concentration is with weight volume percent, also called mass volume percent. Same thing. Mass volume percent and weight volume percent. Weight volume percent and mass volume percent are typically used in medicine when solid is dissolved in liquid. But these are typically used in medicine when the solid is dissolved in the liquid. Now, we're going to come back and do calculations here, but I want to talk about every one of these first, okay? I want to go through all of these first so that everybody's with me and can then practice these more on their own if they want to later. The next one is volume percent. Volume percent. Volume percent is typically used when one liquid is dissolved in another liquid. It's when one liquid is dissolved in another liquid. That's volume. It's typically used when one liquid is dissolved in another liquid. All right, then we also have, so that's two methods of calculating concentration. Another method is, be with me guys, I'm going to do the math with you in just a minute, but be with me here so you're not confused later when you're looking at these. Another method is parts per million. Parts per million can be either mass over mass or volume over volume. So it can be mass over mass or volume over volume. Either one. It just has to be the same unit. So it could be grams over grams, it could be milliliters over milliliters, it could be liters over liters, it could be gallons over gallons. As long as it's the same unit, mass over mass, volume over volume. You could also have ppb, which is parts per what? Billion. Parts per billion. Now, there possibly are some students in here who will eventually wind up working with water treatment plants or doing something in the environmental field, whether it be construction management or not. You may be doing something in the environmental field dealing with contaminants in water. The contaminants in water are measured in what unit? What do you think they're measured in? Volume percent, mass volume percent, parts per million, or parts per billion? Think about what I'm talking about. Contaminants in water. Runoff in a field. Runoff from a factory. Just the water at the water treatment plant that you and I are drinking. What do you think the stuff in the water is measured in? What unit? Parts per million or parts per billion? Correct. Guys, think about that for a minute. Do you want anything in the water that you're going to bathe in or drink to be anything but parts per billion or parts per million? Do you want it to be parts per hundred? What is percent? What is percent? Parts per what? 100. Percent is parts per 100. That's percent. Think about 99. You remember those ball pits? You know, talk about the balls that you used to play in at the wherever. 1 red ball, 99 white balls. What would that be? 1 part per 100. 1 part per 100. Now take 999,000 white balls and 1 red ball. That's what? 1 part per million. Does that make sense? Do you want what's in your water to be 1 part per million or 1 part per 100? Prefer it to be 1 part per billion, right? Pool water, the chlorine, is measured, if I'm not mistaken, I need to double check this, but I'm thinking it's parts per million, but it may be parts per billion, and it's like 2 to 5 parts per million. So is that very much? No, that's not much. If you go into a pool and you smell lots of chlorine, chances are it's too high, because you should not smell it that much if it's the right concentration, because you don't want to have much chlorine in there. It doesn't take much to kill the bacteria. Okay? So this is used a lot in water quality. Okay? Used in water quality testing. And some of you in this room will very likely end up in that field. You will hear these again. If nothing else, every year when you get your water, every year in your water bill, you can go online, or they may even send you a water quality report. Every year, every water company is required to do that. And in that will be the concentrations, and you will see some of these units. You will see that. All right, molarity is the last method of measuring concentration that we are going to use, and molarity is used in, and I'm just going to put science in quotes. It's not something you're going to see much of in the outside world, but you will see it in science classes, in science professions. As a chemist, I would use only molarity. Other occupations that deal with hardcore science are going to use this, but water treatment plants aren't going to use molarity. That's just not something they use. They use parts per million, parts per billion. Now, what's good about molarity, and these can also be used this way, but what's good with molarity especially is molarity is moles per liter, which then becomes a conversion factor. So this is something we're going to use for the rest of this semester. using that molarity as a conversion factor. Those are the only ways to calculate concentration. But the last thing that you do need to go ahead and put down as far as an equation to memorize is the dilution equation. And that dilution equation is C1V1 equals C2V2. What's that remind you of? Gas laws? Okay, so it shouldn't be hard to remember. C1, that means concentration of one times the volume of one equals the concentration of the second one times the volume of the second one. And that concentration can be in any concentration unit as long as this is the same unit. So if it were molarity, that's fine. Both of them can be molarity. If it's mass percent, that's fine too. If it's volume percent, that's fine too. But it has to be the same. Has to be the same. All right, so let's get started. The last thing is the solution stoichiometry, and that's going to be using molarity. So I'm going to hold off on that. That's our very last thing for the semester, is solution stoichiometry. Okay? So let's go back and start the math. And this is what we will be doing Tuesday as well. And then by Friday, I'm sure we'll finish all this up, and we'll see if we even need to meet next Friday. I don't know yet at this point. We'll see. All right, so it says Chloraseptic throat spray contains 0.35 grams of antiseptic phenol dissolved in 25 milliliters of solution. What is the weight, volume, percent concentration of phenol? So what do you know? You know grams of who? Which is what part of the equation? Solute. So here's what I would suggest you do. Put weight, volume, percent equals grams of solute over milliliters of solution. This is what you need to memorize. Weight, volume, percent equals grams of solute over milliliters of solution. And then plug in. So what is your grams of solute? 0.35 grams. What is your milliliters of solution? 25 milliliters. Now guys, I want to warn you, you have to pay attention. Does this say solution or does it say solvent? If it said only solvent, then you can't put it. You would have to add the solvent plus the solute to get the solution. You would have to add them together, and that may happen. You may see a situation like that. Times 100, I forgot that here, times 100 equals, run your numbers. And what do you get? 1.4%, and that is the correct number of significant figures. Yes or no? All right. You do the next one. I'll be quiet and let you do the next one. What did you have to do with milligrams? Okay, so if you don't know how to do that, 20 milligrams, 10 to the third, 10 to the third milligrams in 1 gram equals, so what's that become? Let's see. Is that right? No, this is the 2, isn't it? Yeah. 20.020, is that right? What, honey? Yeah, I did 2.02. So 20 divided by 10 to the third is 0.02. I'm putting this 0 because it needs actually 2 zeros after it because of significant digits. But it's still 0.02. 0.0200 grams over, what's the solution? 4 milliliters, and it doesn't say specifically solution here, but you make the assumption. Times 100. So 0.02 divided by 4, and how many significant digits are you supposed to have? Go back to your original numbers. How many? 2, so what's my final answer? Sorry, I'm not doing my math right. 0.5, you're correct, 0.5%, but it's point what? 0.50%. 0.50%. Yes or no? No? Speak up, honey, I can't hear you. Okay, volume, percent. Pretty self-explanatory. Plug it in. Plug this one in. This one's super simple. Plug it in. All right, what do you get? 13.5 what? 13.5%. Now, what does that mean? That's right, 13.5% of that wine is ethanol. Now, I want to take both of these two scenarios that we've just discussed. We've discussed volume, and we've discussed weight, volume. Do you remember me talking about how I calculate my fertilizer? Do you remember me talking about that in here? So if it's called 0060, which is what urea is, I say that 60 because that really means 60% nitrogen. When I'm doing my calculation, I say that's 60 pounds of nitrogen in 100 pounds of urea. Does that make sense? So in other words, the whole fertilizer urea is not straight nitrogen. It's what? 60% nitrogen. Is the urea in essence a solution? It may not be necessarily, quote, a solution, but is it a mixture? It's a mixture, isn't it? So that 60 is a percent concentration of nitrogen in the mixture, yes? So I say 60 pounds of urea, or 60 pounds of nitrogen in 100 pounds of urea, and does that become a conversion factor? Yeah, I showed this to you in class one day. Okay, now, is this a conversion factor? It can be. This can become a conversion factor. If you know the percentage concentration, guys, listen to me because you're going to have to use this way, okay? If you know the percentage concentration, and you know if it's a volume or a mass volume or whatever it is, that can be a conversion factor, because this means 13.5 what? 13.5 what? What does this mean? 13.5 milliliters of ethanol are in every 100 milliliters of wine. That's exactly right. That's what that means. That's what that means. So if you drink 200 milliliters of wine, then you're getting 27 milliliters of ethanol. Do you follow? Now, let's talk about, for those of you who choose to drink alcohol. If you choose to drink alcohol, what will, quote, get you drunk faster? Wine or beer? Wine. Why? Higher concentration of alcohol, ethanol. That's exactly right. Okay, you can go to whiskey. Whiskey, wine, or beer. Which is going to get you drunk faster? Whiskey. Why? Because it's a higher concentration of ethanol. So then what you have to realize is, and the bottles will tell you this, the bottles will tell you, they will tell you what the concentration of alcohol is. It says it on the bottle. So whatever that is, so give me vodka. What's vodka? 40? Okay, so 40% ethanol in, so what does that mean? If I wanted to drink 100 milliliters of vodka, well, first of all, you've got to get your head around what milliliters are. You've been in lab. Every one of you have had a lab. Do you remember your 150 milliliter beaker? Or your 100 milliliter graduated cylinder? Or did you have a 100 milliliter or just a 50? I can't remember, but you know what the beaker looks like. The beaker is not the best measuring instrument, but it's good enough for what I'm talking about. So it's not, those 150 milliliter beakers are, you remember those little cups that would be at a water dispenser? Any of you ever seen those little cups at a water dispenser station or like a water fountain sometimes, and they might have had a little bitty cup? That little bitty cup was around 100 milliliters. So if you drank 100 milliliters of vodka, how many milliliters of ethanol are you getting? 40 milliliters. Now, something that's higher. What's something that's higher? Say it again. Pepper clear? Everclear? Okay, what's the concentration? So that's pretty much the highest you're going to find. Because you can't get it in, and I'm sure Everclear is going to burn. It will light up. If you've got that much alcohol, it's going to light up easily. You could easily start a fire with that. Okay? So that would be, if you drank 100 milliliters of that, then what would you be drinking? 9 milliliters of ethanol. Okay? 9 milliliters of ethanol. So that gives you kind of a reality, maybe a reality check for some of you. Alcohol will kill you. It also ruins lives. Ask my family. Okay? We won't go to that lecture. But anyway, don't drink. Okay? Don't smoke, don't drink, don't date girls who do. It's an old saying, okay? Or don't drink, don't smoke, don't drink, don't date boys who do, okay? All right. Now, go back to the previous page. Go back to this page. You just determined the amount of phenol in that Chloraseptic throat spray. Tell me on this, what does this mean? What does that 1.4% mean? No, 1.4, give me a unit, not percent. Grams, 1.4 grams of phenol in, nope, it's percent. 100 milliliters of spray. You follow me? Now then, let's talk about this for a minute. Eventually, if not already, most of you will become parents or be somewhat around children, either your own or someone else's. Chloraseptic throat spray is one example of an over-the-counter liquid that looks really good to a toddler or a small child. Why? Because it's sometimes red. Now, does red indicate typically something cherry or strawberry or gonna be candy tastes good? Yes. Some of the cough syrups are red. What happens if little Jimmy gets into it? And believe me, those kids can open bottles. Okay? So what happens if they get into it? What do? What are you supposed to do? What's it called though? There's something specific. Poison Control Center. Call the Poison Control Center. Now, what do you think the Poison Control Center is going to ask you? How much did they drink? Why are they asking you how much they drank? Because then, let's say the lethal dose of phenol for a 20, they're also going to ask you how much does the kid weigh? Or how old is the kid and approximately how much does the kid weigh? So let's just say the lethal dose of phenol is 3 grams per 100 milliliters. That's the lethal, or it's just, let's just say it's 3 grams. That's the lethal dose for a 30-pound kid, is 3 grams. And you have to give an idea, well, how much did they drink? So what do you have to look at? How much was in the bottle to begin with? And the bottle's going to tell you how much is in it. And whoever's on the and you may have the bottle is going to be in ounces. They're going to have to do the calculation. If it doesn't give you milliliters, they're going to have to do the calculation of how many milliliters that would be, or they already have a chart that tells them this in ounces. And then they're going to say, how much did he or she actually consume? How do you determine that? Well, you got to look at the floor. Is there any on the floor? What about their shirt? Is it all over their shirt? You got to figure it out. And then they may say, okay, you got to get to the hospital ASAP, and they got to get their stomach pumped. Or, you know what? They probably didn't get enough to hurt them. Just watch them, give them milk, give them something else, give them a lot of water to dilute it, wash it down, and they'll be okay. But this chemistry math is real, and that's what I'm trying to get you to realize. This is not just, oh, we don't need to know this. This is real stuff. You do need to know it. You do need to know, okay? All right, so does that make sense that you can use this as a conversion factor? And am I probably going to give you something like that? Yes, very possibly if I'm making this much to do about it. Okay? All right, now let's look at one more of these. I want to look at this problem. I'm going to let you do these two, and I want you to, actually, let's do this one. Let's do this one real quick. We got time to do this one. I'll skip the Cydectin. You try this one. It's actually a dimensional analysis problem. You try this one as a dimensional analysis problem. After I do this one, I bet you can figure it out. Maybe, maybe not. This one is easier, honestly, than this one, though. It says, what volume of 5% weight volume solution of ketamine contains 75 milligrams? I don't want you using the mathematical equation volume. I want you to use dimensional analysis and make this a what? Conversion factor. What does this mean? It's weight volume. This one is weight volume, not volume. What does this mean? What does 5% weight volume mean? You just did one like this. 5.0 grams per 100 milliliters of solution. Does that make sense? SOL apostrophe N is solution. So what are you going to, is this going to be your conversion factor? What are you going to start with? 75 milligrams. You follow what we're doing here? If you've understood dimensional analysis up to this point, this should make sense. So you're going to start with 75 milligrams. What are you going to convert milligrams to? Grams. So how many milligrams are in a gram? 10 to the third milligrams in 1 gram. Milligrams cancel. Now what goes on bottom? 5 grams. Good job. What goes on top? 100 milliliters of solution. Because look what it asks. What volume of solution? Run your numbers. And what do you get? 1.5 what? Milliliters. So how much ketamine do you need to give the patient? 1.5 milliliters. Okay? Practice these and look over these extra practice problems, and I will see you on Tuesday.
I feel like the only reason I know maple syrup crystallizes is because my grandparents love to keep bottles for stupid period.